Welcome to this video on nonlinear inequalities. To get into what a nonlinear inequality is, let's start with what a linear inequality is. It's an inequality statement where each side is expressible in a linear fashion, or mx plus b, or a number x times plus a number. For example, this is a linear inequality. Now, this is not what this video is about, but it will give us a good perspective here. You may have seen problems like this before, where you were expected to solve for x by isolating for x. For example, you may have been taught to add 2 to both sides here to cancel out negative 2. Perhaps you've been taught to subtract 9x from both sides to effectively get your x terms together and combine like terms. This is a great strategy. And I would imagine further, you may have been taught to divide by the coefficient of x here, and may even have been taught that there's a special rule for inequalities, that when you divide by a negative, you reverse the direction of the inequality. And what we've discovered here through this linear inequality solving process is that if x is any number greater than or equal to negative 5, the statement at the top of the screen is a true statement. So then what's a nonlinear inequality? Well, it's any other inequality that's not expressible as mx plus b on each side. And that's the focus of this video. Typically for nonlinear inequalities, we see inequalities that have exponents above variables, variables in the denominator, or other things such as absolute values, radicals, logarithms, or any other nonlinear function that one might encounter. For the purposes of this video, we're going to focus on problems that have variables with exponents and variables in the denominator, such as this, or this, or this. In fact, these are precisely the 3 problems that this video will solve. Here's an issue, though. This trick that we learned back in linear inequalities about isolating the variable, while not incorrect, doesn't extend well to nonlinear inequalities. So we can't count on isolating the variable like we might have in the past. And since that doesn't work, it raises a question, of course, what are we going to do with inequalities like this? Well, to answer that question, we need to take a brief diversion away from inequalities and just talk about functions and a fundamental relationship, which we'll call it in this video, between functions and the number 0. To understand this fundamental relationship, let's look at an example. Here's a function. It turns out f of 3 is negative and f of 9 is positive. I recommend pausing the video and convincing yourself of these 2 facts. So these being the case raises an interesting question. In this case, we say that f changes signs between 3 and 9. Why do we say it changes signs? Because when x is 3, the function was negative, and then when x was 9, the function was positive. So if the function changed signs between 3 and 9, one of 2 things had to happen. Somewhere between 3 and 9, the function either had to be 0 or it had to be undefined. This is just a mathematical fact about functions. If a function changes signs between 2 values of x, one of those 2 things, or possibly both, has to have happened between those 2 values. In this case, what happened is that f of 5 is undefined. Notice the math. Here's another function. It turns out that g of 1 is positive and g of 4 is negative. Please pause the video and convince yourself of both of these facts. So if the function went from positive to negative, we say it changed signs between x equals 1 and x equals 4. Well, again, General theory of functions tells us that if a function is going to change from positive to negative, it either needed to be 0 or undefined. Now, there are exceptions to this rule about functions, but they're not things that we really encounter too often. And so we won't consider the rare exceptions to this in this video. So that must mean that g was either 0 or undefined, somewhere in between 1 and 4. And it turns out, at a number about 1.7-ish, or radical 3 to be more precise, this function had a value of 0. Notice the math. Now in this video, you're not going to be plugging in random numbers to functions and expecting them necessarily to be 0 undefined. There's more of a process that will unfold here. But for you to understand the process, you have to understand this basic fact about functions. So we care very much about where a function is 0 and where that function is undefined. And that's going to be the basis for the explanation of the problems in this video. Let's look at an actual example. Here's the first of 3 examples we'll be doing in this video. Ultimately, what we want to do here is solve for x, which means we want to find all values of x for which this is a true statement. Well, it turns out, we haven't gotten to the answer yet, but it turns out there are infinitely many values of x which make this statement true. But there are also infinitely many values of x which make this statement false. And our goal is to find all infinitely many values that make this a true statement. And that's what we're embarking upon here when solving this inequality. But we just got done with a long speech about functions relative to 0. There's no 0 here, and there are no functions here. So why did I bring that up? Well, to give you a slightly different perspective on this problem. First, what I'm going to do is subtract 28 from both sides of this inequality. That gets me the 0 on one side that I need. And when I'm solving a nonlinear equality, I want a 0 on one side of the inequality. One or the other, it doesn't matter which. Because what I like to do is make one side be 0 and consider the other side my function. We'll call this f of x because it doesn't matter what letter we choose to call it. Now, this is how I approach nonlinear inequalities. To solve this inequality is exactly the same as to say, for what x values is this function negative? Why negative? Well, the function has to be less than 0 for the inequality at the top to be true. So I've changed my perspective on the problem. I want to think about where, for what x values, this function, may see it in green, for what x values is this function 0? And that's the question I'm going to embark upon right now. Well, to do that, I like to ask myself 2 questions. When is the function equal to 0, and when is the function undefined? Because you'll recall our main concept from earlier is that for most functions, at least the ones we consider in these nonlinear inequalities, the only way that a function can change from positive to negative or negative to positive, the only sign switches can occur with a function being 0 or undefined between them. So these are the 2 questions you always want to ask yourself after setting your inequality to 0. So let's take the top question first. When is this function 0? Well, the function is 0 whenever its expression equals 0 is solved for a particular x value. And you should remember, or maybe you remember, enough basic algebra to see when this function is 0. Hit pause if you need to review all of that. The idea here being, we have found the only 2 values of x for which this function equals 0. So we've answered the first question. Second question, for what values of x is the function undefined? Well, f of x is a polynomial function. It's never undefined. In other words, it's defined for all real numbers x. In other words, you could plug any x in and get an answer. So there are no such values that concern me here. So now that I've answered my 2 questions, let's analyze the number line. Remember, our goal, as we've made it for ourselves, is to find what values of x make f of x negative. And we're going to use a little trial and error and deductive reasoning here. First, I'm going to start by picking a random number of 3. I'm going to plug 3 into my function. Here is the arithmetic. Hit pause if you're interested in the particulars. What have I just discovered? I've just discovered that when x is 3, the function is negative. But it was my goal to find out what x values made the function negative, because those will be solutions to our top inequality here that we see. So 3 is a solution to this problem, because f is negative when x is 3. Well, great, we found one of them. But wasn't our goal to find all of them? So what should we do? Plug in literally every number between negative infinity and positive infinity? Well, of course, that's not possible. So we'll have to rely on some clever deductive reasoning in place of that option. So I'd like you to ponder a thought here. Let's consider the entire open interval from -4 through 7. Open means not including the endpoints. Any number between -4 and 7, I'll just put a dot here to represent literally any number in that interval. At that particular x value, whatever it is the function negative or is the function positive? Well, you might think at first, well, I don't know. I'd have to know what the number is. That's not true. Let's first ponder the question, is the function positive there? Turns out it can't be. Why not? Well, because, follow this weird logic. If the function were positive there, then there'd be a sign change between that number and 3, somewhere in here. But wait a minute. If there were a sign change between that number and 3, that would mean that in between, at the purple arrow, somewhere in there would either have to be the function having a value of 0 or being undefined. But wait a minute. The only two places where the function is either 0 or undefined are -4 and 7. So there can't possibly be a sign change from that number to 3. And therefore, I conclude that f must be negative there as well. That was some tough logic. I recommend you may want to rewind the video and hear that again. Nonetheless, I'll move on either way. So, what that means is wherever that number is, the function has to be negative at that dot. Again, the logic here is this. Function can only change from positive to negative or negative to positive with a 0 value or undefined value in between. But -4 and 7 are the only places where the function is 0 or undefined. And therefore, -4 and 7 are the only places where this function can change from positive to negative. And if it's negative at 3, then it's negative there, and it's negative there, and it's negative there. And in all of these places, the function has to be negative, simply because it was negative when x is 3. Now, there's an infinite number of points in there, and we don't want to draw a ton of dots. So we generally tend to just shade that part of the number line. That shading represents that any number between -4 and 7 will result in the function being negative and therefore be a solution to our original inequality. Just to be clear, what we've done here, we picked one single number between -4 and 7. We found out that the function was negative there, concluded it therefore must be negative in that entire interval, and therefore that entire interval is part or all of the solution to our original inequality. But we haven't tried anything outside of this interval, so let's sample a few points there. Let's randomly just choose 10 as a test point. If you plug 10 into the function, arithmetic will show that you get a positive answer. But we're looking for all places where the function is negative as a solution to our inequality. If the function is positive when x is 10, then it can't be a solution to our inequality. But wait a minute. If the function is positive at 10, meaning when you plug 10 into the function, you get a positive answer. Then wouldn't you also get a positive answer anywhere in this interval, such as here, or here, or here, or here, or here, or here, or here? So what have I deduced? Because this function is positive when x is 10, it must be positive on the interval from 7 to infinity at any x value. And therefore, none of those numbers make the function negative, and accordingly, none of them are solutions to our original inequality. So if none of those numbers are solutions, we erase them all. We don't write anything for these numbers are not solutions. The one portion of the number line we haven't examined yet is over here. I'll pick a random number over there of negative 9. When you plug negative 9 into the function, arithmetic will show that you get a positive answer. But we're not looking for places that make the function positive, because we need places where the function is negative to represent solutions to our original inequality. So that tells me that negative 9 is not a solution to our original inequality. But functions can only change from negative to positive or vice versa at the 0 value or undefined value locations, in this case negative 4 and positive 7. So if the function is positive when x is negative 9, then it's going to be positive anywhere in this interval. The function will be positive here and here and here and here and here and here. And the conclusion, therefore, is that if the function is positive everywhere in that interval, then there can't be solutions to our original inequality anywhere in that interval, from negative infinity through negative 4. So I'll erase all of that and tell myself there are no solutions to my inequality over there. So let me summarize what we've concluded. We plugged in negative 9 here, and because it was not a solution to the original inequality, we concluded there are no solutions in the interval from negative infinity through negative 4. We plugged in positive 3 and found that it was a solution to the inequality, and therefore everything on the interval from negative 4 through 7 is a solution to our inequality, hence the shading. And we plugged in 10 and concluded that because 10 was not a solution to the inequality, there couldn't be any solutions in the interval from 7 through infinity. So, have we considered all parts of the number line? Well, more or less, yes. We haven't actually considered the transition points yet, the negative 4 and 7 themselves. So is the function negative in either of those places? Well, it can't be, because we concluded earlier that the function was 0 at those two places. If the function is 0 there, then it isn't negative. If it isn't negative, then those two numbers are not solutions to my original inequality. So we've now analyzed the number line in its entirety by picking one number from each of the three intervals and by analyzing the endpoints or transition points themselves. If you take all of the information that we've discussed about this problem, the conclusion is that this function is negative exactly when x is any number between negative 4 and 7. But remember, the function being negative, we decided, was equivalent to the inequality being solved up here, the original one. And therefore, the conclusion leads us to the fact that that inequality must be true exactly when x is between negative 4 and 7. So, what is the answer to this inequality? Well, because I prefer interval notation, I'll write the solution to this inequality is the open interval from negative 4 through 7. Remember, the comma in this answer represents through. And that's the solution to this first inequality. Here's our second of two examples. Suppose we want to solve this inequality. Again, these problems are best served when you're comparing a function to the number 0 because then you can have discussions about positives and negatives. So what I want to do here is subtract 2 from both sides, because now I'm comparing a function on the left side to 0 on the right, and that's mentally easier to deal with. But the function on the left side isn't really simplified, so I think this problem would go better if I simplified the fraction minus 2 that you see on the left. To do that, I'm going to get a common denominator and combine like terms and ultimately simplify. It's been a while since you've done rational expressions like this. Hit pause and analyze the details. So what I've done here is convert this inequality into a simpler inequality to analyze based on the fact that it has 0 on one side and a simplified version on the other. So for comparison's sake, we're going to call this function g. And now what I've done here is I've changed the question of solving this inequality to being equivalent to asking when the value of g of x is either positive or 0. You'll notice I got that because it says g of x greater than or equal to 0. So let's set up a number line and begin the investigative process to find out when g of x is either positive or 0. Well, remember, g of x, or any function of study in this topic, can only change signs when the function is 0 or undefined. So we want to ask, when is g 0 and when is it undefined? Let's start with the top question, when is g 0? G is 0 when the formula for g equals 0. But here's a strange but easy concept. A fraction can only equal 0 when the numerator is 0. That's literally the only way a fraction can ever equal 0. And so if the numerator is 0, x must be negative 1. And so I've answered my first question. When x is negative 1, g is 0, and I've placed it on my number line as a dividing point. For the second question, for a function to be undefined, among other things, the denominator would have to be 0. So for this function not to exist, x would have to be 4. 4 would make the denominator 0. I'll place that on my number line as a transition point as well. And so what I have on my number line here are the two places where g can switch from being positive to negative. It can't change signs anywhere else. So now let's analyze this region by region, starting in the center for no particular reason. I picked a random number in the center. There's nothing special about 0. But now that I've picked this number, let's plug 0 into g of x. Here, g is negative, you'll see by the algebra shown. But remember, I'm looking for places that g is either positive or 0. If g is negative here, then it doesn't match that criteria. So if 0 doesn't make g negative, 0 is not a solution to our original inequality. And if 0 isn't a solution, then this entire interval from negative 1 to 4 can't be a solution either. So I can rule out that entire interval as having any solutions. Here's another seemingly random number. I'm going to plug 6 into g of x, and I got a positive answer. But I was looking for places where g is positive. So I've just showed that g is positive when x is 6. There's nothing special about 6. Remember, g can only change from positive to negative at a transition point. The transition points are negative 1 and 4, and therefore g is not only positive when x is 6, g would be positive anywhere in the interval from 4 through infinity. That's equivalent to saying that any number 4 through infinity is a solution to our original inequality. So I found infinitely many solutions in the open interval from 4 through infinity. There's one interval we haven't tried yet, so I'll pick an arbitrary number from there. Might as well choose -2. When we plug -2 into the function, we get a positive answer, which is exactly what we were looking for, places where g is positive. And since g is positive there, that means that -2 is a solution to the original inequality. But if -2 is a solution to the original inequality, so is every number from -infinity through -1. And so now what I've discovered is out of the 3 intervals created by the 2 transition points, 2 of them contain all the solutions, the one on the far left and the one on the far right. I still, however, have to give some thought to the transition points itself. So what about x equals -1? Is that a solution to the original inequality? In other words, is the function 0 or positive there? Well, we discovered that the function was 0 there. That was where this transition point came from. And therefore, -1 is not only a place where g is 0, but it's a solution to the original inequality. And finally, analyzing 4. Is 4 a solution to the original inequality? Well, not really. Well, not at all, because g is undefined when x is 4. And if the function is undefined, it can't be a solution to an inequality. So there's no reason to include 4 in our set of solutions. In fact, if you look at the original inequality, imagine plugging in 4 for x. You would get undefined greater than or equal to 2. That doesn't make any sense. There's no reason to think that 4 is a solution to something when you can't even plug it in the first place and get a numerical result. So in conclusion, we've discovered that the function g is positive whenever x is less than 1 or greater than 4, and also that g is 0 when x is -1. Here's a restatement of that conclusion. The original inequality is true when x is less than or equal to -1, or x is greater than 4. In other words, the solution to our original problem is the union of intervals -infinity through -1 inclusive of -1 and 4 through infinity. Let's look at one final example. Suppose we're trying to solve this inequality. Again, no mention of functions or 0 here, but because this is nonlinear, notice the exponents, it seems like a good idea to have one of the sides be 0, so we can use the positive-negative comparison that we've been using to solve these nonlinear inequalities. So to make one of the sides 0, I'm going to add 9x to both sides. Simple enough. So just for discussion's sake, we're going to call this our function and call it h. You don't have to name the thing to solve it, but you want to think of it as a function, whether you call it h or not. Because now the question of, is this inequality at the top true, is equivalent to, for what values of x, is the function h either negative or 0? I got this because the inequality on the left side says function is less than or equal to 0. So I really am solving two different issues here. When is the function less than 0 and when does it equal 0? So to embark upon this journey of discovery, let's make a number line and analyze the different regions. As usual, the way we find these regions is by asking ourselves, when is the function 0 and when is it undefined? Let's start with when it's 0. The function h is 0 whenever the formula equals 0 has a solution. So now we have to use our prior algebra skills to solve this equation. What I did to solve it is I factored out an x, and then I factored the remaining trinomial as x minus 3 times x minus 3, also known as x minus 3 quantity squared. And I realized just by looking at this that the two solutions are going to be x equals 0 or x equals 3. And so those are the two values for which this function is 0. If that algebra eludes you a bit, then you may want to go back and think about the equation on your own, or hit pause and do that now. But there we have it. We have the values of x for which the function is 0, and I'll put those on my number line for further analysis. Next, I have to ask, when is the function undefined? Well, this function is a polynomial, and polynomials are never undefined, or they are defined for all values of x. So there's no such value there to worry about. So what I now have is my transition points on my number line. When I say transition points, I mean those are the only two places where this function could potentially change from positive to negative. And that's pretty important when it comes to the analysis. Because remember, I'm trying to solve all infinitely many values that are going to make this inequality true. And to do that, I really don't have time to plug in infinitely many values. So we're going to use this shortcut of the transition points. First, we'll randomly start in the middle interval, let's say with x equals 2. When you plug 2 into the function, which is the same as plugging it into the left side of the inequality. Remember, if you never called this function h, it wouldn't matter. Just plug 2 into the left side of the inequality and see if it's true. Well, I did the arithmetic on scratch paper, and I got a positive answer, as you can see here. But remember, h being positive there does me no good, because I'm looking, well, it does me some good, but it isn't the solution to the problem, because I'm looking for places where the function is either negative or 0. If it's positive, then it isn't negative or 0. Now, the fact that the individual number 2 is not have a negative or 0 function value is the same as saying 2 is not a solution to my original inequality. But the beauty of the transition points of 0 and 3 is this. If 2 isn't a solution to my original inequality, then nothing on the interval from 0 to 3 will be a solution to my inequality. And therefore, I can conclude that there are no solutions in the interval from 0 to 3. We'll cross that whole interval off of our list. Next, I'll go to the interval on the right for no particular reason, other than I've got to go somewhere, and pick a random number from there, let's say 5. And we'll plug 5 into the function, or the left side of the inequality. Same thing. Well, it turns out we get a positive answer there as well. But I'm not looking for values of x that make the function positive. I'm looking for values of x that make it negative or 0. So not only does 5 make the function positive and is therefore not a solution to our inequality, more importantly, because the function can only transition from positive to negative at the transition points, then the function h must be positive on that whole interval. And therefore, there are no solutions in that interval as well. So it seems the first two intervals I've tried, I've failed. But that's fine. There doesn't necessarily have to be a solution at all. There are definitely problems with no solution. To see if we have a solution, let's try our third interval. I picked a random number from there, say -1. And I'm going to plug -1 into the left side of my inequality. Well, I did all the work on scratch paper, but the point is, I got a negative answer. And I was in fact looking for places where the function would be negative, so I've found that. But not only is h negative when x is -1, By the transition theory, that a function can only transition from positive to negative at the points 0 and 3 in this case, I can conclude that the function must be negative on the entire interval, from negative infinity through 0. So not only is -1 a solution to my inequality, every number on that interval will be a solution to the inequality. So I've now found infinitely many solutions, which is typically the case for an inequality. What I haven't done yet is test the transition points themselves. Are 0 and 3 going to be x values for which the function is either negative or 0? Well, yes. We already discovered that 0 and 3 were places where the function was equal to 0. And therefore, both 0 and 3 are solutions to my original inequality. So let's summarize the results that we found in our discovery while examining the number line. We found that if x is less than 0, the function is negative. And we found that if x is 0 or 3, the function is 0. So all of these are solutions to the original inequality. I've restated it by combining x less than 0 and x equal to 0 as x less than or equal to 0, but essentially, this is what I've discovered. I like my answers in interval notation, so the final way I'm going to represent this is the closed interval from negative infinity through 0. Notice the bracket to indicate inclusion. Joined in the union with the number 3 itself. Notice those are braces, and that's not interval notation. So what is this saying? We're saying essentially that 3 is an isolated solution where numbers on either side of it don't work. Remember, the interval to the left of 3 and the interval to the right of 3 didn't contain solutions to this inequality. But we discovered that the number 3 itself, just the number 3 over there, was a solution. So when we express it using interval notation, one of the components is not an interval. It's just a 3 in braces, meaning the number 3 itself. And that completes this lesson. Thank you for watching.